two dependent samples, also known as matched pairs. So we will be doing hypothesis testing and confidence intervals. And to be matched pairs, there has to be some kind of relationship, such as before and after measurements from the same subjects. IQ scores of husbands and wives, twins could be used. And so some of the notation we'll be using, D represents the individual difference between the two values. And we'll find that with the graphing calculator. And then if you see mu D, that's the mean value of the differences for the population of all the matched pairs of the data. So D bar is the mean of the differences for the paired sample data. So this is for the sample. And then this D is once again for the sample data. Now think about N, number of pairs of sample data. Each data set has the same number of values. Before and after are the same number of values. Has to be the same number of values. The test statistic we could use, which I'm not going to, but we could use, is this. If you want to do it by hand, then use tables, that's fine. I'm going to use technology. This margin of error for the confidence intervals is one you have probably seen before, maybe in a previous video. For hypothesis testing, that the HO will always be that the population difference of the matched pairs will always be 0. And then H1 will vary. It could be greater than, it could be less than, it could be not equals to 0. One of those three. So let's get started with some examples, just to give you an idea. So here we go, we have data values, and I'm going to use the p-value method primarily. Our alpha is 0.05, and like I said, the null hypothesis will always be, the population difference will always be equal to 0. And then our H1, or alternative hypothesis, will have the population difference. Let's see what this one is. It says the mean score is not affected by the course. So that's a not equals 2. Let me make it a little bit easier to see. That's a not equals 2. So this is the before and after for a test of abstract reasoning. The before a course and then after a course, after a logic course. So does the course make a difference? Is what's going on. So we're testing the average score before versus the average score after using this sample. With the graphing calculator, this is not the easiest thing in the world to do. There's no built-in feature, straightforward, like there is in StatCrunch, which is what I'm also going to use. So with graphing calculator, what you want to do is you want to go to Stat and Edit, and I already have those values in. But here's the thing. I can't go to Stat and then Test and use a two-sample t-test. There's nothing in there. So I have to go back to my reasoning up here is that the D bar, that's the difference for individual data values. That's going to be the mean value, the differences. So what that means is I got to find D for each pair of data values. So I got to find the difference of each one of these. And as you can tell, it's 1, 6, 5, 11, 10, -4, -2, 1, 7, and 2. Now you can do that individually and use that for L3 if you want to do it that way. So I could just type those in, like 1, and then 83 minus 77 is 6, and then 75 minus 70 is 5, and that's totally fine. But there might be a little bit better way, and so let's see if we can find what that might be. So you could do this. You could do second 1, which is L1, and then minus second L2, and then store into second L3 and hit enter. And it brings up those values. And if I go to Stat, enter, then it calculates all those for me without me having to do them individually. So it does make it a little bit easier to do it that way. So that's 1, 6, 5, 11, so on, so on, so on. So now when I go into Stat and to Test, I'm going to go to number 2, the t-test, and then use the data. And we're going to keep the mean as 0, and then make sure it's on L3. Mine already is, because this isn't the first time I've looked at this. So keep it on L3 if that's where you store the differences, because we're looking at the differences only. Like I said, we're looking at the differences minus the population. So the sample difference, sample mean minus the population mean. So that's what this is doing. It's doing the population mean minus the sample, or the sample mean minus population mean. Sample mean, sample difference mean minus population difference mean. Frequency, keep it on 1 on this calculator, and then keep it on not equals, and click calculate. So some things to look at or to notice, we do have a t-score here, t-statistic, that'd be like 2.37 if you need to use that. We do have a p-value, probability value of 0.042, and then we really don't need anything else. Degrees of freedom will be 9 in case you're wondering, because 10 minus 1 is 9. If I use StatCrunch, StatCrunch is way easier because it has a feature that we can use. I've already got the value sorted in var1 and var2. So if I go to stat, tstat, see that paired? That's what you're looking for. Column 1 would be var1, column symbol 2 is var2. Keep it on not equals, just click compute. You see those values. If I round up 2.37 and then 0.0422 if I want to put in the extra 2. So you tell me which one is easier. I know which one is, just admit it. And so what we have here is a conclusion that since 0.042 and our alpha level is 0.05 is less than 0.05, you reject HO. There's evidence to support that the population difference is not 0 and the fact that they are different. And I'm going to type that out. There is evidence to support that the mean difference of the populations are different. Something like that. They're not actually equal, they're different. I'm not saying they're bigger or smaller, I'm just saying they're different. That wasn't the test. The test was, are they affected or not? So they are affected. So you can say to support the mean difference of the populations are affected by the course. Confidence interval method, that's where we're going to have to use the t statistic. And then we're also going to use alpha is equal to 0.05. So we're going to use, well, we have to find a confidence level. And so to find a confidence level, I'm going to draw my picture of a T. Not quite normal, but pretty close. And since it's not equals, that's 2 tails. What that means is that this alpha, which is the same thing as area, in both tails to combine is 0.05, which means that's going to be 0.95 because 1 minus 0.05 equals 0.95. So our confidence level is 95%. Now I don't need that t equals 2.37 for this because I was thinking about rejection regions, but we do need the 95%. So we're going to find the confidence interval, I should say, the 95% confidence interval. So I'm going to go into my graphing calculator again. I'm going to go to stat, test, then I'm going to go to t interval, which is number 8, t interval. Then keep it on data, L3, 95%, so I'm going to keep it at 0.95, and click calculate. And we get 0.162, if I round up to 3 places, and 7.24. And since you gotta look at the fact that 0 is not in the confidence interval, since 0 is not in the confidence interval, so when you see this, when the 0 is not in there, but 0 is in our HO, but 0 is not in there, that means we can't conclude that 0 is in our HO, which means we have to reject our HO. You can think of it like this: if 0 were in the confidence interval, you can say we have evidence that keep the 0, which means we would have evidence to keep the HO. But since it's not, we can't keep the HO, so we reject it. You don't actually keep anything. I'm just trying to give you a way to think of it. If I go to StatCrunch, I should have stayed in there with the paired, but it's okay. I just used edit. 0.95 compute to 0.162 and then 7.24 for round off. Not too bad. Not too bad at all. For this example, I won't be using the graphing calculator because it takes a little bit too much time to type in, so I'll just be using StatCrunch. So what we have here, we have times before training and times after training. So let's start with the alpha. And we need our HO and our H1. So once again, the mean difference will be 0. They're the same. And then we have to take into account what's going on here. When you're training for a race, you want your time before, you want it to be greater than your time after, because you want the time after to be less, because that means you're faster. The faster you finish a race, the faster you are. So it should take less time. So time before should be greater than. So this should be greater than 0. Got that? And that's actually probably the hardest part of this problem, recognizing that this is a greater than. So the time before is going to be greater than the time after, because we should be decreasing our time after our training. So like I said, I'm using StatCrunch, and I already have the data values in var3 and var4. At least I thought I did. Yeah, I did. There they all are. Okay, so you can see they're in 3 and 4. So when I go to T-stats, paired, this time click on var3, var4, and this one is a greater than, so it's a greater than, and then click compute. And so once again, if you need to see the T statistic, that was given to be 2.23, because that may be a question in your homework. And then the P value is given to be 0.0306. So I'm just going to come over here and write it down. Our alpha is 0.05. So since 0.0306 is less than 0.05, we reject HO. And what that means is that training works. How's that? Because since we reject HO, that means that the mean difference, that means that's pretty much wiped out. That means there's evidence to support that the times have improved, or that the training helps improve the athlete's time, because the time before is greater than the time after. That's what's going on. So when you reject HO, think of it as there's evidence to support the H1, which means that the difference in times, that the time before is greater than the time after. There's evidence to suggest that. And since the time before is greater than the time after, it means their time is slowing down, or using less time, not slowing down, but using less time to finish the race, which means they're running faster, which means they're improving. There's evidence to support the training helps. There's all kinds of ways you can say it. I'm just thinking in real life terms. Confidence interval method. So once again, we got to look at that point. Alpha is 0.05. But this time, be really careful when you want to draw a picture. But be careful at the confidence level. So it's greater than would be there. That would be 0.05. However, we're dealing with confidence intervals, so we're looking at two tails, which means you have to look at the 0.05 over there also. So we're looking in between, because confidence intervals always look in between. So that's the same thing as 1 minus 0.05 minus 0.05, which is 0.90. And that's our confidence level, 90% or 0.90. And we need that because when I go to StatCrunch, I'm just click on Edit. This time I'm going to go to confidence level and just change that to 0.90 and click Compute. And our confidence interval is 0.2144, 0.21, you can see that here, 0.2144 to 2.661, 2144. Comma 2.661. And once again, since 0 is not in the confidence interval, and it's not, those are two positive values, since it's not in 0, we mark that out, the HO out. We reject HO. It's not in there. Can't accept it. Can't keep it. You have to reject it. It's not in there. Since 0 is not included, we can't assume that the difference is 0. 0 is a possibility. There's evidence to support that there's an effect in the times. Question number 3. So what we have here, once again, we have training, gymnast training before and after. So in this one, before I do any work at all as far as technology goes, you need to be aware that we want the before scores before and after. If you think about it, you want the after scores to be greater, don't you? These should be bigger than those, so the mouth always eats a bigger number. So the after should be bigger than before. If you're a gymnast, the after scores, you want those to be higher. It's not like running in a race. You want the times to be shortened. You want these scores to be higher. So the before score should be less than the after. So we do have our alpha of 0.01. Our HO is the same as it has been. Our H1 is going to be less than 0. So we're going to determine, is training effective? The training technique, is it effective? Now I am going to do the graphing calculator. Hopefully these won't take that long to type in, but I will make mistakes, so you might want to fast forward through this. Stat, enter. I'm going to show you how you do this. Clear, clear, clear. This may be the last time I use a graphing calculator in this video, because they take a little time to type in. Oh, make sure you use a comma or a decimal there. And hopefully you're watching and oh, don't do that either. Dangers of using this kind of a calculator. Hit the wrong thing. I'm going to go up here and check to make sure that everything is typed in correctly. 9596 9496 9696 9594 9596 9699 9795. So remember what I did? I did this to get the L3 and want the difference. So I did L1 minus L2 store and L3, hit enter. It brings up those values. Let's go to stat edit just to check. 9.5 minus 9.6 is negative 0.1, 9.4 minus 9.6 is negative 0.2, and so on and so on. So now I'm going to get out of there, go to stat test number 2 for the t-test, keep it on data. I'm going to keep my list of L3. This one is a less than, so I need to go back up there and hit enter, change it to less than, then enter for calculate. And you'll see the t score, the t statistic, negative 0.0. if I go two places, 88, the p-value is 0.206. Is it 3? Or let's go 4. Stat crunch, just to show you. I think I had those in here already. I don't know where I'm at right now. Stat crunch. Okay. Probably saw a list of my notes. So that should be 9.5 and 9.6. Okay. So let's go to stat, t-stats paired, and then var1, var2, and just hit compute. And there t-stat, nope, see, I hit the wrong one. Remember, these are 5 and 6, or 5 and 6, 5, 6, yeah. You probably don't want to do that. You probably want to keep all yours in var1 and var2. Negative 0.88, and then p-value. What did I do with the calculator? Interesting, isn't it? So let's see. Did I do? Yep, I did something wrong. I got in a hurry and oops, I did again, as Brittany would say. I have to make sure that I use the less than. See, learn from my mistakes. I didn't do that. Less than. Now do you see it? 0.2064. See that? Yeah, watch out. Watch every little thing. Even I make mistakes. Hey, happens. Learn from what I do wrong. It's the less than. Less than. But anyway, since 0.2064 is greater than 0.01, what do? We fail to reject. Fail to reject. Just too big. Could have happened by chance. So there's no evidence that the training technique is effective in raising the gymnast scores. There's no evidence to support it. Not saying it doesn't, just don't have any evidence based on this sample. Okay, now this last one, I'm just going to use stat crunch just to save a little bit of time, but you know how to do it in the graphing calculator. L1, L2, then the difference, and then do the confidence interval. Or maybe I should do it in the graphing calculator. Probably should. Let's go ahead and do it. Stat, edit. I'm just going to clear all these out once again. Yes, there are other ways to clear, but I like doing it this way. Make sure. Okay, here we go. 168, 180, 157, 132, 202, 124. I gotta watch how I type this. And by all means, take out your calculator and type them in like I am if you happen to have a calculator. And if you don't have a calculator, then fast forward. Don't watch this. Wait, look until I get to stat crunch. Nothing says you have to watch it, especially when I do like what I just did. Do you see what I just did? Delete. I went to go to L2. 162. Now you really have a reason to fast forward, don't you? If you don't have a graphing calculator. Trust me, I can type a lot faster than this, but be really careful with this calculator. Let's go and check, make sure. 168, 162, 180, 178, 157, 145, 132, 125, 202, 171, 124, 126, 190, 180, 210, 195, 171, 163. Once again, I like to do this. I like to go to do it like this: second L1 minus second L2 store L3. So when I go in the stat edit, you'll see the difference. 168 minus 162 is 6. 180 minus 178 is 2. You can do it over here manually if you wanted to. However you want to do it. This time we're doing t interval only. So what was that, number 8? And data. What is this? It's a 99% confidence interval. That's our estifying, by the way. Negative 0.6247, comma 20.403 is a confidence interval. And as always, I will use StatCrunch. And I think those are already in 7 and 8. Let's go to stat, tstat, paired, 7 and 8. And this one is a 99% confidence interval. Enter. Let me move it over here. I see well, I did see negative 0.62. Negative 0.62. It's right there. 20.403. 20.403. Checks out. And that is it.